Another way to quantify noise in an oscillator is to talk about jitter. Jitter is a time domain measurement rather than a frequency domain measurement, so it's normally measured on an oscilloscope. The plot on the right there shows a typical jitter plot, and here what you can see is a number of waveforms overlapped onto each other to form a solid block, because the time base has been pushed out to such an area that it looks solid on the scope plot. And in the top right you see an eye diagram, and in the top left you see some measurements. They're jitter measurements, and what you can see is things like a mean value, a max, a min, a peak to peak, and a standard deviation for various different types of jitter. And that's very typical of jitter. It's a statistical analysis of all of that data that's been measured there. To make a jitter measurement, you're going to need a scope with a very high sample rate, very high bandwidth, because you're trying to measure the exact changes in the rising edge and where that occurs over repeated steps. So yeah, we have to spend a lot of money to buy scopes with very, very high bandwidth. And what I have learned from this is that you can be careful when you adjust any setting on the oscilloscope. Very often the bandwidth jumps back to some default value, and you have to manually turn the sample rate back up to the maximum. So just a little tip there when you're playing with this equipment. We found that to be the case in most of our scopes. So when we look at jitter, it's a statistical measurement, as we said, of the overlapping pulses, and you're trying to establish how good they are to being perfect. Jitter can be broken into two areas. We can say that there are random jitter, which is unpredictable electrical noise and typically follows a normal distribution and can be caused by thermal noise in the circuit or things of that nature, as opposed to deterministic jitter. Deterministic jitter is more like the spurious response we saw in the frequency domain. It's predictable, it's reproducible, it can often be attributed to something very specific, and it has a non-normal distribution. And then from that there is total jitter, which is the sum value of the two. And as I said before, all these values are then discussed in their statistical terms. So what's the peak value, or what's the standard deviation, or some such like that. Jitter is used by our customers because often in a digital system one is trying to calculate a total bit error rate, and a good oscillator will reduce the jitter contribution within the whole system. So if we can get the oscillator jitter lower, then everything else's jitter will be lower, and so the total bit error rate will be improved. That's the objective here.